Today I'm going to complete what we did in part 1 and go on to solve the global localization problem using the extended Chalmers filter, but for the case of unknown data assignments. So first, the table of contents. Now, first of all, I'm going to give a recap of part 1. What did we actually solve and what is actually to come next? Then I'm going to discuss why bother with data assignment at all. Of why it is important and how does it actually appear in practice. Then I'm going to give a formulation of the data assignment problem, which is going to be a maximum likelihood estimation problem. I'm going to talk a little bit about how to solve it and how the hypothesis would look like during the EKF update, then the full algorithm, and finally the results of applying to the same landmark map that we used in part 1. Now I'm going to give a recap of what we did in part 1. So basically in part 1, we actually solved the global localization problem, but with known landmark assignments. So we were able to let the robot localize itself in a known map, but we also assumed that given the measurement matrix at any time instant, we were able to tell that measurement Z1 was, for example, to landmark I1, measurement Z2 was coming from landmark I2, and measurement Zn came from landmark In. So we basically assumed that each landmark had a certain, let's say, unique identifier that we were able to pick up while we were doing the measurements. Now, this assumption might not be too strict because in some cases we can actually engineer the features to have certain, identifying indices. However, this would require certain modification or quite an extensive modification on the on the environment, which would be quite restricted to maybe, factories or certain types of, laboratory experiments. And it could be actually quite expensive to have an ability to label all of these landmarks. And this is where the unknown data assignment problem comes from, in which we assume that we have no idea how each measurement was generated. We don't know this association between the measurement and the landmark, and we'll have to figure them out as we move. Now I will answer the question of why bother at all with the data assignment problem. So let's have, for example, this setting right here. We have a robot at position x1. It can see landmarks I and k, and it generates measurements z1 and z2. Now this is another scenario where the robot is at state x2. It observed landmarks q and j and generated the exact same matrix of measurements Z1 and Z2. Now, this might happen because the configuration of the landmarks with respect to the robot are identical in both cases. This might happen at all. Now, the important question of which actually is true. Now, why is this important? Because, associating the measurement to the correct landmarks would quite reflect on the update step of the Cannon filter. For example, assume that our real robot is at x1. However, we actually assume that we associate these measurements to q and landmarks q and j. Now, this would have a profound effect on the update step of the Cannon filter because now the filter would lead to believe that the robot is actually at position x2 rather than x1. So associating the correct landmarks to the correct measurements is actually of vital importance because it will actually help us tell where the robot is by associating it to the correct landmark location or map location. Now, of course, I should mention that sometimes there are certain maps that have a lot of symmetry. Now, and in these cases, the ability to associate these measurements to the landmarks is quite difficult, nearly impossible to actually differentiate in practice, even in practice. So in this case, we will have to keep different hypotheses to to take into account the possibility of having more than one location until we actually converge to the true location by taking more measurements. Now I'm going to discuss how to formulate this data assignment problem. Okay, we're going to give a maximum likelihood estimation. Now we're going to formulate the data assignment problem. And one of the most prominent methods to do this is to phrase it as a maximum likelihood problem. So first, for each hypothesis Q and for each landmark and measurement pairs I, G, we compute the log likelihoods, which is the measurement likelihoods, but in logarithmic form. We have seen such numbers used and computed in the update step of the Cannon filter, and the expression is just the same. For a reminder, we can see that the Zi is the measurement that is predicted using the ith landmark and the state of the hypothesis. Si is computed actually in the same form. Hi is the Jacobian of the measurement function evaluated at the state of the Q hypothesis and at landmark I. And also notice here that the annovation is actually the difference between the jth measurement, the real jth measurement, and the predicted Zi. So this actually computes for all pairs. These innovations, takes this, weighted distance and, takes the logarithmic form. So given these likelihoods, we can phrase the data assignment problem as follows. So basically, we are going to find a subset of indices, let's say k indices, from the measurements, from the measurement space, and certain corresponding indices j, which are functions of the alphas, such that the sum of the likelihood is actually maximized. So in simple terms, we are going to associate a subset of the measurements to another subset of the landmarks, such that the likelihood of this assignment is actually maximized. Notice here that I made a sum. The sum is because we have logarithmic likelihoods. Of course, if we had normal likelihoods, it would be a product, but as we said, for numerical issues, this would be quite beneficial. So that's how we frame our problem. We turn to the problem solving the data assignment problem after we just formulated it. And how do we solve it, and how does the hypothesis actually evolve during the filtering steps? So I should mention that this problem, the way we just framed it, is actually a combinatorial optimization problem. Some of the famous algorithms to solve them are the Hungarian algorithm, auction, and GVC. We usually don't just find the best assignment, we find top K assignments and keep track of all of them, in case we just miss something, or in case there's a highly symmetric map and we just want to to keep all the options available for later updates. And in this case, we use something called Mert's algorithm, which finds the top K assignments. It's actually the one used in this video. Now, of course, each assignment will be represented, in our case, with a pair of Z and S. Z, as we said, is a subset of the measurement matrix, and S is a vector of corresponding landmark indices, which generated those measurements. Now, in this case, we could use now those in the update step of the Kalman filter because they are known correspondences. Now, the hypothesis would look something like this. So let's say before or at the beginning of the iteration of the Kalman filter, we have n hypothesis. Okay, so when we are doing the update, hypothesis 1 would split into k different hypotheses. Each one is updated with one of the top k assignments. Okay, so this will multiply the number by k, of course. It could be k, it could be less, depending on how many of those assignments are actually viable. And the same will apply to all other hypotheses, and the same for hypothesis n. It would be updated into k different versions. Each one has an updated step using a certain assignment of the top k assignments. So this would mean that the number of hypotheses would actually grow multiplicatively at each time step, so exponentially basically in time. And as we mentioned, we will have to keep a maximum hold of the number of hypotheses by doing pruning, capping, merging, any type of reduction method that you would like. Now we are going to talk about the full algorithm in which the components will just stick together. So I should just mention that many of the steps in this algorithm have been outlined in the first video. I'll just not repeat them for clarity and brevity. So this would mean that the prediction and the update steps will be used just as names or blocks, and the full equations can be found in the first video. So now we repeat the following steps for all hypotheses, I from 1 to n. First of all, we predict. So in this case, we predict the hypothesis using the usual, prediction steps in the Kalman filter. Then, using the measurement matrix that we just observed at this time instant, we find the top k assignments. Now, of course, each assignment would have, ni correspondences, I from 1 to k. Now, these can be found using, as we said, Mert's algorithm. It actually has a certain function in MATLAB. It's called assign k best. So it's actually quite available. You could just look it up. It's easy to use. Then we're going to perform the following steps. So for each of these assignments, as we said, each assignment is represented by a ZG and SG. That is a subset of the measurement matrix and the corresponding landmark indices. So first, we update the state of the current hypothesis using the spare, ZG, SG. This can be easily done using the same steps found in the update equations in the first video. We just use the measurements and the corresponding indices, and it will all be good. Then we create a new hypothesis. The new hypothesis would have a state that is equal to the updated state of, that is updated using this assignment. And it will have a weight that is given by the previous weight of the hypothesis and the likelihood of this assignment, which could be given by the product of, which could be given by the product of the measurement likelihoods, which are also computed in a previous video. Now, after all of this, we'll have a huge number of, we will basically multiply the number of hypotheses by k, so we'll have to normalize and prune the weights. So normalization is actually used to keep the state density as a valid PDF. So we will have to just normalize the weights. Normalizing logarithmic weights is actually what is done, and it has some few tricks, can be easily found anywhere to ensure no underflow or no overflows. And then we prune the weights or reduce the weights using any type of method viable. Now we will show some of the results of applying this algorithm to the same landmark map as before. So again, this is the map. The red dots are the landmarks. The pink is the robot, green is the sensing range, and this is the nominal path, the blue one. Notice that in this case, we have the black one is actually the real path, that is due to the noise. The blue one is the nominal path, and the same applies. The robot is the pink, and the sensing range is the green one. Now this right here will show the results of the filtering in red, and then the real path, which is in black. You can notice that for the first few iterations of the first segment of the path, the filter actually failed to converge correctly to the real path. Now this could be due to different types of problems. My most probable guess is that because the map was randomly generated and was actually just a bunch of feature points scattered randomly in a map, there could be some places that give similar measurement patterns, and this had made it quite difficult for the filter to converge in the first few steps. This means that it might have had multiple hypotheses with quite competing weights, weights of the same order, and this made it quite difficult for the filter to approach a correct estimation. However, look and see that at the end of the path, the filter was able to correctly recover the real path of the robot. Now, the same will have to hold for the angular estimation. The first few steps of the filtering, the angular error was actually quite huge, and then it dropped to nearly 6 degrees in the final stages of the path. Now, you can see here that we potentially solved the global localization the global localization problem using unknown data assignments. So in this case, we do not know which landmark generated which measurement, and we used the Mertens algorithm to find top K assignments and store such possibilities in new hypotheses. So this is quite a robust method. I should also mention that in practice, as I was trying to apply this algorithm, I found that it was actually quite sensitive to the motion model noise, which is quite quite plausible. It was actually also it required maybe a high number of hypotheses to converge correctly. Now, this is probably a caveat of the EKF because it just approximates using Gaussian mixtures. Maybe using other types of filters could be more beneficial because they can capture different types of densities. So some of the final thoughts and future ideas, as you said, I could try other types of filters. Specifically, I'm looking forward to trying the particle and Markov filters because they could capture any type of density. Theoretically, they capture any type of density and are able to recover from the kidnapped robot scenario. So these are actually quite interesting and could be applied in future videos. As we said, some of the sophisticated measurement models could be used to handle spurious endless detections, the random finite sets formulation for measurement modeling, and finally, we could also look into more robust methods for data assignment. In this case, we use the maximum likelihood. There could be other methods. Haven't quite explored the literature on this problem. There could be other types of problems that could be quite solvable in a better method. So again, thank you very much for listening and following these videos. As usual, give me your opinions in the comment section of how interesting you found the localization problem. If I should go into more depth, maybe to explore different types of features, could be, for example, line segments, and look into more types of sensors, like, for example, LIDARs or these types of ideas. Thank you very much, and that's it.